Hey everybody, today we're going to talk about the inverse matrix and the identity matrix from section 7.3, but before we do that, let's just do a little checklist on what are we allowed to do with matrices. Can we add them? You bet, as long as they have the same size and dimensions. Can we subtract them? Same rules though, they have to have the same dimensions or size. Can we multiply them? Sure, that's what we just did before. That's a little bit tougher, but we can totally do that. Remember, the inner numbers have to match, and the solution, the answer, has the dimensions of the outer numbers. Can we multiply by a scalar? Oh, sure, absolutely. That's pretty easy. You just distribute the scalar inside the matrix. So really, I feel like the only type of operation that we haven't done yet is divide. Can we divide two matrices? And that's the next question. Well, I'll give you good news and bad news. The bad news right off the bat is that we can't. There's no way to mathematically divide matrices. We have to find another way. But the good news is, it's actually pretty easy, but we just can't divide it. So we'll find another way that's going to be called the inverse. Now, before we talk about an inverse matrix, we need to kind of go back to a little bit of Algebra 1 first. So here's our section title, if you want to write that down in your notes. But I'm going to take you back first to Algebra Land. Take a break from matrices for just a second. Remember we talked about in chapter P, what's a number that I can multiply 2 by and get 2 back out? Or, on this side, what do I multiply 5 and get 5 back out? And it is the number 1, exactly. And we call that number the multiplicative identity, or we can just call it the identity. Because when you multiply a number by 1, you get that same number back out. So that was called the multiplicative identity. Okay, fine. But over here now, back to matrix land, we need that same kind of idea of the number 1. What does the number 1 look like in matrix land? So if I give you a matrix A here, a 2 by 2, look at this matrix here. It's called the I matrix, which stands for the identity. I is the identity. Okay. Well, let's see what happens. Just for the heck of it, can we find what is A times I and what is I times A? Well, let's give it a try. I'll go back a page and try that. So off to this side. A was 2, -1, 3, and 0. And I, what we're calling the identity matrix, is 1, 0, 0, 1. Let's see what A times I looks like. Now, first of all, we should double check if we're allowed to. This is a 2 by 2, and the I matrix is also 2 by 2. So since the inner numbers match, we're good to go. And we can see that our outer numbers are going to be the size of the answer. So my answer should be a 2 by 2. All right, remember rows by columns. Here we go. Let's take the first row of A and the first column of I, multiply, and I should get 2. If I do on the top right, how about row 1 on the left and column 2 on the right, I should get -1. If I work on the bottom left, that'd be row 2 from A and column 1 from I. That should be 3. And for the bottom right, the last entry should be row 2 from A and column 2 from I. Multiply, and I should get this. Do you notice what we got out? Did you see? Yeah, we got A back out. So that means we took a matrix A, we multiplied by something, and we got A back out. Therefore, I is the identity, the multiplicative identity, but for matrices. Now, just to see what would happen, what if we reversed it? What if we did I times A? Again, that is legal because it's a 2 by 2, both of them. Now, I'm going to rewrite this so I can actually see it in order. Here is my I. I'm going to multiply times my A matrix. All right, rows by columns. That means I should get a 2 by 2 answer, and the row from the left and columns from the right, I should actually get 2, -1, 3, and 0. And again, do you notice what I got back out? I got A back out. So therefore, we can call I the identity. And based like you see here, this I matrix, the identity matrix, is basically the matrix version of the number 1. This basically means the number 1. where if I multiply any matrix into it, Or if I multiply it times any matrix, I will get that same matrix back out. It is the number 1. So we call that the identity matrix. Notice what it looks like. Do you notice that it's basically made up of 1s on the down right diagonal, and then everything else is just a 0? Oh, that's interesting. What if we had bigger ones? Well, look at these. We can call these by their size or dimensions. This is I2 because it's a 2 by 2. Can you see why this is called an I3? And therefore this one would be an I4. But notice what they all have in common. All 3 of these identity matrices have 1s on the down right diagonal. All of them. And then everything else is made up of 0s. Every other entry besides that are all 0s. And that's what makes it basically equal, again, to the number 1 in matrix land. Somehow, this combination of 0s and 1s in those exact spots make everything work out like you're multiplying by the number 1. All right, so there's your introduction to the identity matrix. Now we're getting closer to the inverse, so I'm going to take you back again to just algebra land. If I said, hey friends, can you solve this equation for x? How about 2x equals 6? Now I bet you could probably go in one big step and get to the answer. How? Oh, divide by 2. But if you said the word divide, that makes me a little nervous because in matrix land, remember, we're actually not allowed to divide. We don't know how to do that. So we really can't jump and take this step. So can we find a different way? Instead of dividing by 2, what if we actually did this? What if I multiplied both sides by 1/2? So if I multiply by 1/2 on both sides, that's the same idea as dividing by 2. And just see what happens. Using the associative property, I'll gather the 1/2 and the 2 together. Because when I multiply 1/2 and 2, I get 1. Remember, 1 is like the identity. Because 1 times x is just x. And when you multiply the 1/2 on the right side, you get 1/2 times 6, which is n fine. So I know this seems like a longer way to solve for x, but when we translate this into matrix land, it's going to make a lot more sense. Because we can't divide, we're going to find another way of multiplying by its reciprocal, or in matrix land, its inverse. So in general, here's what it's going to look like, friends. Again, we're still kind of in algebra land, but if I'm taking this equation, I'm going to solve for x. Instead of dividing by the a, we're actually going to multiply both sides by the inverse of a. And notice that we do it on the same side. I'm doing it here on the left, and I'm doing it over here on the left. That's kind of important if you remember how matrices work. If you multiply left to right, it could be different than right to left. So we're going to keep the same direction. And then by the associative property, I'll gather the a inverse with its a. And when you multiply a inverse by a, you just get the number 1 back out. So that gives you x. Notice on the right-hand side, a inverse times b, well, we don't know what that is because they're not numbers, but they just stay as they are. All right, now, after that little jump to algebra land, let's go back. Welcome back to matrix land. Now, all these capital letters are matrices, remember. So if I give you this equation, I say, let's solve for x. Remember that x is a matrix. We need to solve for the A matrix. And it'd be really easy to divide by matrix A, but we cannot divide. So instead, look what we're going to do, friends. We're going to multiply both sides on the left by the A inverse. When I multiply by the A inverse, and I use, again, associative property, A inverse and A multiply, and they give you 1, but remember we didn't call it 1, we called it the identity matrix. That's why you get I. And I times x is like multiplying by 1, you do get x back out. So we did solve for x there using matrices. Now, if I keep going on the right side, because these don't simplify yet, this is what we have. So I want to get you the idea of the fact that we can't divide, so we're going to have to solve by using the inverse. Now we're going to do that a little bit later on. But for now, let's talk about how we can actually find the inverse. But I want to give you one more thing here on the bottom. Really important that whenever you multiply a matrix by its inverse, whether it's from the left or the right, you will always get the I matrix back out. Remember that's some version of 1s in the diagonal going down right and 0s everywhere else. You know, before we find inverses, can we just prove that really quick? Let's just show really quick on this quick example here. can you show are matrix A and matrix B inverses of each other? Meaning, from our previous page, if I take A times B, do I get the I identity or I matrix back out? Let's find out. Okay, let's take A times B. If I do A times B, here's A. That's multiplied by B. Okay, it's legal because they're both 2 by 2s. Here's your A matrix, here's your B matrix. And I should get a 2 by 2 matrix back out. So let's see what I get. Again, rows on the left and columns on the right. Why don't you try this on your own, pause the video, and come back and check with me and see how you did. Okay, if I take the rows on the left and the columns on the right, my top left one should be -1 plus 2 is, on the top right, I should get 2 plus a -2. This is looking promising. On the bottom left, I should get -1 plus 1. And on the bottom right, I should get 2 plus a -1. And there it is. That's our friend, the I or identity matrix. So are they inverses of each other? Yes, they are, because A times B gave us the identity matrix. Could we do B times A and check? Yes, but we don't have to. We don't have to here. It works. Great job, folks. All right, let's actually now find out how can we find the actual inverse of a matrix. So I'm going to skip ahead a little bit here. Now, we can only find the inverse of a matrix if it is a square matrix. It must be a square matrix if you want to find the inverse. If he's, say, a 2 by 3 or a 4 by 1, we cannot find the inverse. These do not have inverses because they must be a square matrix. All right, so we'll start with 2 by 2s. If I give you a matrix here, how about the A matrix is A, B, C, D? There's 3 things that you're going to find here, friends. The first thing you need to find is you want to find the determinant of A. What is that? The second thing you're going to do is you're going to scramble your A matrix. And I'll show you what that means in a second. And then the third thing is to use the formula that you see here on the left. Okay, friends, can we find the inverse, the determinant first? Yes, absolutely. That was our down right minus down left. Fine. And then look what we did to scramble our matrix. Look and see between the original, this is A, B, C, D. Look what happens between this matrix here and what we're calling the scrambled matrix over here. What did we do? Well, it looks to me that if A was here, he's now here. If D is here, he's now here. Okay, B was here, and he's still kind of here, but look what happened to him. I think I can say the same thing about C. C is there, he's still there, but look what happened to him. So it looks like the down right numbers, those two numbers switch. So A and D completely switched with each other. The down left, those two entries, they stay, but you just flip signs. Not the numbers, just flip the signs. So if they're negative, they become positive. If they're positive, they become negative. Okay, so they don't move spots though. They stay where they are. The down rights are the ones that switch. Okay, and then we plug it into this formula. Here's your formula, friends, for the inverse of a matrix. Once you find a determinant, it becomes 1 over the determinant of A. That's what those bars mean. And you're going to multiply that as if he's a scalar into our scrambled matrix. Now, what if? What if you found the determinant, but the determinant equals 0? Well, that's a little dangerous, friends, because remember, over here, we're going to divide by the determinant. If you try to divide by 0, we can't do that. It's illegal. It's not defined. So if by chance your determinant of your matrix is 0, that's not defined, which means A does not have an inverse. If the determinant of the matrix equals 0, he does not have an inverse. All right, let's put some numbers into it so it'll make a lot more sense. Here we go, friends. For number 1, for matrix A, can we find the inverse of A? If possible, again, because maybe the determinant is equal to 0. All right, so three things we're going to do. First of all, can we find the determinant of A? All right, we do down right minus down left. That would be 6 minus a positive 2, which is equal to 4. So my determinant is 4. And then if I scramble my matrix, that means I'm going to switch these two numbers and change the signs of these two numbers. And then we're going to use our formula. Okay, here we go. Up here on top, a little bit of space. For number 1, A, and I'll use the inverse notation, A inverse is, the formula says it's 1 over the determinant of A, which was 4, multiplied into our scrambled matrix. So the 3 and the 2 switch, and the negative 1 becomes positive, and the negative 2 becomes positive. All right, now we're not done. We have to multiply that scalar in, and when we do that, let's go ahead and simplify our fractions if that happens. So multiplying by a scalar is easy, right? You just multiply every term by that scalar. So 2 times 1/4 reduces to 1/2. 1 times 1/4 is just 1/4. Notice I'm using fractions here instead of decimals. It's a little bit easier to use. On the bottom left, I have 2 times 1/4 again is 1/2. And then 3 times 1/4 is 3/4. And that is my answer. That is my inverse of A. Now I could actually prove that this is the inverse by taking A, the beginning one, multiplying by inverse, and if they are inverses, what should we get? Shall we test this out? I'm going to do this right now. Feel free to skip if you don't need to see it. But I'm going to take my two matrices here, I'm going to multiply them together and see what I get. Let's do this up here on the top left. A, my original matrix, times my new inverse that I found. That is 3, -1, -2 and 2, times my inverse I just found, which was 1/2, 1/4, 1/2, and 3/4. Multiplying with fractions are always a little tricky, so just be careful and be patient. I know it's a little rough, but you guys are good. You can do it. All right, rows by columns. I should get, in the first one, 3 times 1/2 and -1 times 1/2. That's 3 halves minus 1 halves is 2 halves, or 1. On the top right, I should be 3 times 1/4 plus -1 times 3/4. That's 3/4 minus 3/4. This is looking good. Bottom left, how about -2 times 1/2 plus 2 times 1/2? That's -1 plus 1. And finally, -2 times 1/4 and 2 times 3/4. So that's -1/2 plus 3 halves. That's actually 2 halves, or 1. Well, look what we did. We got it back out. We got the number 1, or the identity matrix, back out. So our inverse is right. Do you always have to do this and check this, folks, when you find your answer? No, but it is a great way just to double check if you're ever on a quiz or test or on your homework. You just want to see if you got it right. You can also always multiply your answer to your original A matrix and see how you do. All right, on your own, can you try number 2? Can you find the inverse of this matrix? I'll give you about 30 seconds. First thing we should do is find the determinant. And I should get 3 times 2 minus -1, -6. That's a positive 6. Uh-oh. Uh-oh. Our determinant's equal to 0. Remember what happens if our determinant's equal to 0? Can't do that. So therefore, there's no inverse, because I'd be dividing by that determinant as part of my formula. So before you think about scrambling your matrix, go ahead and check and see what the determinant is, because if the determinant is equal to 0, you don't have to do any more work. This one does not have an inverse guaranteed. And that's the introduction to how to find the inverse of a matrix, along with its friend, its identity. Next time, we'll talk about what's coming up next, where we're going to use the inverse to actually solve systems of equations in a really, really cool way. Great job today, friends.